Greetings from University of Notre Dame. My name is Prashant Kamat, Professor of Chemistry and Biochemistry and Radiation Laboratory, and also concurrent professor in the Department of Chemical and Biomolecular Engineering. Today I will be talking to you on light energy harvesting with semiconductor nanostructures. Before I proceed, I would like to thank U.S. Department of Energy, Office of Science, Basic Energy Sciences for supporting our research for more than 3 decades. Let's begin. There have been 3 recently game-changing developments to achieve clean energy. This has happened right in front of our eyes, and many of us even fail to recognize how much advance we have made in terms of generating renewable energy, and it is becoming part of our everyday life. Take, for example, solar cells or wind power. Both of them now compete for grid power. So they are becoming as economical as fossil fuels. So in many countries, they became a significant portion of grid energy. The second aspect is storage batteries. The storage batteries also have seen a drop in prices, especially lithium-ion batteries. You are seeing now in cars, and people are talking about using for grid energy storage. So developing these kind of technologies involve a lot of research, and whatever we have done in the last 10-20 years has benefiting us in implementing these technologies. Third and most transformative aspect is in this renewable or clean energy development is LEDs, or light emitting diodes, or display devices as we refer it. Just in 2010, only 1% of lighting was done with LEDs. Today this amounts to about 30-35%. By 2025, they are expecting 95% of the lighting in the world will be governed by the light emitting diodes. So that's why you see everywhere now street lights to big lightings are all done by light emitting display devices. The reason is simple: they consume less energy to give you the same amount of light. So the energy saved is energy gained in many respects. So these 3 factors have allowed us to get into the next phase now to achieve clean energy. Just to give an example of how much drop in solar is in this next slide, you will see is a clip from Bloomberg, and they say that every time the world's solar power doubles, the cost of panels falls 26%. So you can see here how much drop in price occurred. On the right hand side, you see in 2008 to generate a watt of power cost little over $4. Today it's barely 22 cents. Again, you see the steep decline in near the 2010, as well as also another decline around 2013. So this makes us a very interesting case for using renewable energy or solar energy for generating electricity. So having said that, most of today's solar power is generated through silicon. Silicon is a very energy consuming process. To prepare silicon from sand, you need very high temperatures, so that means it has a large carbon footprint. Now we can see in this slide the design of semiconductor nanostructure based thin film solid state solar cells. They are solution processable. They require only low temperature, and most of the cases you can make them under ambient conditions with no special clean room or any other requirement, which we call it the benchtop technology. Another one is because of these aspects, it requires low energy demand for production and hence lower greenhouse effect with this technology. So that's why these kind of semiconductor nanostructures are being studied in various laboratories to come up with new and more economical as well as less greenhouse gas emitting processes to make this technology. So we call it as a more emerging transformative PV technology. Before I start, I would like to tell you about how these semiconductor nanostructures are shaping, how it all started, and where we are today. The birth of renewable energy is basically seen in early 70s when there was OPEC oil embargo came into effect, which sort of shook Western countries with shock. They never thought that there will be a day where fossil fuels will be, or the fossil fuel supply will be limited. So suddenly people started thinking about alternative energy, and one of them that came into mind was photosynthesis. The nature does it so well, so why can't we make it in the lab similar to the plants? So the word artificial photosynthesis came into play, and that involved various photo-induced electron transfer reactions, exploring new light-absorbing materials and dyes, molecular systems. Those things continued. Another field that came into play was semiconductor photoelectrochemistry. This became a very popular research topic in those days, in the late 70s as well as in 80s. Another offshoot of this project was also photocatalytic properties of semiconductor particle systems. And here are some of the people I got influenced when I was doing my graduate work, and they had some very nice visionary ideas to utilize renewable energy through semiconductor materials. In 90s, the semiconductor nanoparticles were extensively studied and new processes were explored. One of them was environmental remediation. These were what we call photocatalysis, like for example titanium dioxide. If you have a titanium dioxide paint coated on a wall or a window, it can clean all the organics, either that is deposited on the surface or even in air. So it became a very industrial process, and if you go to Japan, you will find many of these applications for cleaning air you will encounter. The other one was solar fuels, or converting light energy into chemical energy. This is essentially the same semiconductor principle, where we have say for example titanium dioxide particle on which you can put a metal particle and an oxygen generating catalyst like iridium oxide, and essentially by shining light you can generate these electron hole pairs, which can in turn split water to make hydrogen and oxygen. So this was again led to exploration of many new materials, and this research is still continued today and extended to carbon dioxide reduction and nitrogen reduction. So I will not be talking on this topic, but mostly focus on the photovoltaic aspects. Another major breakthrough came in 91 when Michael Gretzel and his co-workers published a paper in Nature on the dye-sensitized solar cell, where they used the mesoscopic TiO2 films on which they put a ruthenium tris bipyridyl dye as a sensitizer. When you excite this dye, you get this electron transfer TiO2, and the redox couple, in this case iodide triiodide couple, regenerated the system. so that basically what was happening is this light is absorbed by the sensitizer and is just converting light into electricity through this process. So this gained a lot of moment in the next 20 years or so, and today we have about 13 to 14% cells have been demonstrated with different sensitizers and different redox couples. A major turning point came in 1993 when a group of researchers from MIT published a method to prepare size-selective semiconductor nanocrystals. As you can see from the figure, they prepared different size particles from 12 angstroms to 45 angstroms in diameter. And what it showed was you can use chemical synthetic procedure to prepare a semiconductor particle that exhibit size-dependent absorption and emission properties. You can see on the left-hand side there is the blue color, which is the smallest particle, and red color, which is a larger particle. Essentially, these particles were same material, but they were showing the ease of synthesis of quantum dots or semiconductor nanocrystals by hot injection method has revolutionized the way we make the semiconductor nanostructures and utilize for a variety of applications. This method is still being used today to prepare different types of semiconductor materials. In the next slide you will see which is referred as CDS-SC quantum dots. In this case, one can vary the composition of sulfur and selenium and prepare different band gap material. So the ratio of sulfur and selenium in this material controls how the band gap is. For example, cadmium sulfide has a large band gap and cadmium selenide has a lower band gap, absorbing well below, say, 650, 660 nanometers. But by tuning their composition, one can get the intermediate band gap. So this is another strategy one can use to vary the band gap of these materials. What started as just a academic exercise in making these particles, today one can see in practical devices. One of the most popular place where you see quantum dots is in TVs. All modern TVs now have these indium phosphide quantum dots, and here are the two examples from LG and Samsung. They usually refer as quantum dot display, and they are being used to enhance the color of the pictures that are being displayed. It just shows you how these kind of materials can be very useful other than the energy applications. So this kind of a basic research has a lot of rewards that comes on our way when we continue these research activities. Here is just examples of what else one can do with these semiconductor materials, is to bring two or more different semiconductor nanostructures. So this is just a glimpse of some of the work that we have involved in utilizing various semiconductor nanostructures. Take, for example, on the top left, where we are using titanium dioxide and a square-N die and a cadmium selenide. We call as a molecular linkers or bifunctional molecular linkers to attach two particles. In this case, the square-N die that we use has a thiol group that attaches to cadmium selenide, and another end it has a carboxylic acid that attaches to titanium dioxide. When you excite the light with the visible light, the cadmium selenide absorbs high energy light and then transfers its energy to the square-N die, which in turn transfers it to the TiO2. So similarly, one can build various semiconductor nanostructure hybrid assemblies, and we can study their energy transfer processes, electron transfer processes, and essentially making them a better performing system. So that's what we have been focused on. So let's Let us now see quantum dot solar cells. Between 2000 and 2012, there have been significant activities to utilize these quantum dots or semiconductor nanocrystals for light energy harvesting. So they utilize the same principle as dye-sensitized solar cell and trying to make quantum dots as sensitizers in these solar cells. The advantage of these kind of a solar cells being tunable band edge that offers the possibility to harvest light energy over a wide range of visible light. Another one is because their size is small, the hot carrier extraction becomes very easy in these systems. And third, another interesting property was multiple carrier generations in solar cells, especially systems such as lead sulfide, which is the very low band gap materials. One can use high energy photons to generate more than two pairs of charge carriers per photon in this system. So this has gained much more attention, and let's see now how we make these quantum dot solar cells. There are two types of quantum dot solar cells. One is liquid junction, another one is solid state solar cells. Both operate on the same principle. As you can see here, it consists of an optically transparent electrode on which you put metal oxide substrate, on which you put sensitizing quantum dots, and then in the liquid junction we use a redox electrolyte to regenerate the system, whereas in the solid state we use a whole conductor, so it could be spirometad or an inorganic whole conductor like copper thiocyanate, copper iodide, those kind of systems, which helps to regenerate by scavenging the excess holes in the semiconductor system. And finally on the top you have counter electrode and to assemble this solar cell. So this is the basic principle of the solar cell, and the way it operates, you can see here in this cartoon we have a TiO2 particle to which a cadmium selenide is attached. The cadmium selenide is a low band gap material and absorbs visible light. Upon excitation you generate electron and hole pairs. The electrons get injected into titanium dioxide, which is extracted by a conducting glass electrode. The holes are scavenged by the redox couple, and this way the particle is regenerated. Now how do you see these processes? The injection of electrons from cadmium selenide to TiO2 is an ultra-fast process. On the top right corner we show you a method that we use. We call it the pump probe spectroscopy, where we bring in a laser pulse to excite this cadmium selenide and try to see the changes in the absorbance with time, and that gives you a time scale how this absorption changes or how the material is restored at what rate. The left top corner tells you a photoelectrochemical cell, where we can study the photocurrent, photovoltage measurements to study overall efficiency. In the next slide you will see a performance of a quantum dot solar cell. This was originally published in 2008, where we showed that the size quantization effect, that is the dependence of absorption and electronic properties on the size, is reflected in the performance of the solar cell. The smaller size particle has a higher band gap, which is represented in the yellow color, and that absorbs high energy, whereas the large particle size are red in color, they have small band gap, and they absorb all the way until the beyond 600 nanometers. As you can see here, these 4 electrodes show the size dependent performance, and this plot, what is referred as IPCE, is incident photon to charge carrier efficiency or external quantum efficiency in these systems, and is plotted against the wavelength, basically showing you the response of these solar cells. Another interesting aspect was the higher efficiency that we see with the small size particle, what you call the excitonic peak, and it decreased as we increase the size, and that we attribute to the band gap and more driving force for having this electron into the TiO2. So again, on the top right corner is shown what they call a sandwich cell we make with these kind of systems. We continued our studies, and at that time, this is 6-7 years back, we got about 5.4% efficiency, and shows you how we can get a very stable performance in these systems. And furthermore, we studied a variety of processes. Although it looks very simple to make a solar cell, the processes that follow the light excitation makes this system very interesting. For example, once you shine the light on cadmium selenide, there is a charge separation represented by E and H, and the electron get transferred to TiO2, and then although all the green arrows show the positive processes that favor the photocurrent generation, the red arrows that are dictated here shows you the loss of electrons to these recombination processes, either with the holes or with the redox couples in the system. So this is one of the reasons why these cells perform rather poorly in this system. Another aspect of our study was to see how fast this electron transfer occurs. As I said earlier, we use pump probe spectroscopy, which follows the absorption changes in the system following a laser pulse excitation. We use extremely short pulse laser, which is about 150 femtoseconds, and the negative delta A or negative delta absorbance you see corresponds to disappearance of the original absorbance as you separate these electron hole pairs. With time, these electron hole pairs recombine, and we see a recovery of these bleach or the negative absorbance, and comes back to this original state. So what happens when the same material sits on a titanium dioxide which accepts electrons? So you are opening another new pathway shown in the red arrow, which is essentially a drainage of electrons or charge injection into the TiO2 particles. Now we can also do the same experiment what we did before without TiO2 and compare the recovery rates. And the bottom right panel, you will see there is a bleaching recovery trace. That is, you monitor the absorbance at one fixed wavelength and then see how the time it changes. And clearly, with and without TiO2, there is a difference in the kinetics, and based on this difference we can calculate the rate constants to be of the order of close to 1.95 times 10 to the 11 inverse seconds. We further studied the size dependent electron transfer rates, and indeed when we decrease the size by a factor of 3, we saw an increase in the electron transfer rate of 3 orders of magnitude in this one. And in fact, we went ahead and used these 4 different size particles and 4 different type oxides. In this case, silica served as an insulator where we cannot transfer electrons, so that is sort of our reference, and other zinc oxide, titanium dioxide, tin oxide served as electron acceptors. So we measured the rate constant for electron transfer, and in this right hand panel it shows our data points and a fit of many state Marcus theory, showing the dependence of electron transfer rate constant on the free energy of the difference that is driving the electron transfer process. Today there have been other semiconductors. We call them ternary semiconductors. This 1,3,6 chalcopyrite structure is derived from the fact that the group 2 element in the zinc blinded structure is substituted by group 1 and 3 elements, and here you see copper indium sulfide, copper indium selenide, silver indium selenide. So variety of different materials have been prepared by just having this combination of 2 different metal ions. And they also have shown the size dependent properties. That means that band gap can be tuned by just varying the diameter. So this ternary semiconductor offers new ways to design and also tune the properties of the semiconductor nanocrystal. So this is another emerging field that can have more impact in the coming years. Recently, there have been great interest in developing what they call perovskite solar cells, and it has become a game changer. And the reason is simple, because in a very short time, its efficiencies have risen from 3% in 2009 to about 24.3% in 2019. So this remarkable improvement in efficiency can be seen through the understanding of various other technologies that have been developed over the years. The first one you can see here, dye-sensitized solar cell, or DSSC, on the top left corner, where here we had about 10 micron thick film and which sensitizers were absorbed, and this has over the years solid state DSSC, extremely thin absorber cell, and perovskite solar cells. Now the perovskite solar cells uses less than 500 nanometer thick active area, and that absorbs all the light. And more than that is the efficiency has gone up to all the way 24% in this case. As with the interest of the people working in this area also have surged, which is also can be seen by the number of perovskite papers published and the citation they receive over the years. Lead halide perovskites are essentially a hybrid organic-inorganic, or also all inorganic materials, where they have a formula ABX3, whereas X, where here refers to as halide ions. A typical prototype compound is methyl ammonium lead iodide, and in this case you can see here the lead iodide forms this complex and generates this cavity in which a cation gets inserted, and this cation is typically used as cesium, methyl ammonium, and formamidinium. So these fit in very nicely in these cavities, and they interact with the lead ions in this structure, whereas other cations are either too small or too large and cannot be accommodated. There have been some efforts to use materials like rubidium or dope them with these materials to see some changes. How do you make these films? And it is very simple. One can make in any lab. You mix lead iodide and methyl ammonium iodide in chlorobenzene and stir for 2 hours at 70 degrees, and you get a yellow colored solution. Spin coat it and then anneal it. Within minutes you will see this black colored film, and the steps are shown in the bottom how the color change occurs. You can also use two-step method where you first spin coat lead iodide and then expose it to methyl ammonium iodide. So both give same type of films, but most of the studies today they work with this single step method. In the lab we have made, this was a few years back, we made about 16% efficient cell. Just show you how the performance of this cell looks like. This is the left top corner, shows you the what you call JV characteristics, where you are supposed to get both forward and reverse cycles same plot, but there is small hysteresis, and this has been a topic of many discussions, but the good cells show very minimal this hysteresis effect. You also have a steady state PowerPoint position here which can use to calculate the efficiencies. Another thing we also evaluate is external quantum efficiency, and this external quantum efficiency is again number of electrons generated per number of photons incident, on the solar cell, and it varies because of the absorption changes. It varies from 800 to all the way until about 320 nanometers. You can see how the performance, and once you integrate this one, the result, you should get values of current density close to the short circuit current that you see in a JV characteristics. The morphology of the cell you can see here in the bottom left corner. This is the large crystals are fluorine doped tin oxide, and these are what we call as a conducting glass, on which we put a compact TiO2 layer followed by mesoscopic TiO2 and methyl ammonium lead iodide, and then we coat with a whole conductor of spirometad, and then you put a layer of gold, and that is it. So this is the anatomy of a perovskite solar cell, and when you shine the light, these perovskites become active, the electron flows to the TiO2, and the holes travel to the whole conductor to the gold electrode, giving you the photocurrent in this system. This is just to give an example how a solar cell works in this case. There have been stability issues, and but this has been now addressed by incorporating triple cation, where they use both formamidinium, methyl ammonium, and cesium as the cations in a different proportion, and they are able to get very stable solar cells. Now let's move back to the perovskite quantum dots. Just like you discussed about cadmium selenide quantum dots, you can also make cesium lead halide perovskite quantum dots. And the picture here shows you the cesium lead chloride, cesium lead bromide, cesium lead iodide, and also the last one is a manganese doped cesium lead chloride. And these will have a different band gap energies. As a result, they absorb in a different region of the visible spectrum and also emit light. So many of these materials emit close to unity in terms of emission. So they are bright glowing nanocrystals, and that has created a lot of curiosity trying to use them for energy harvesting applications. And most of these are cubic structure. You can see here on the bottom right TM image showing you very well-defined crystal structure of this material. How do you synthesize? Again, it's a hot injection method. You use lead bromide in octadecene, oleic acid, oleamine, and then inject cesium oleate at relatively milder high temperature, in this case 120 to 140 degrees Celsius, and you get this bright colored solution, which you can again purify, wash off the ligands and other things. Variation in this approach also exists. Then we spin coat on the top of the electrode, and we can repeat the cycles if needed to get higher absorbance, and then we put this film in between the glass slides for spectroscopy regions. And then here is the TM image on the left hand side of the crystals that we prepared by this hot injection method. But when you spin coat and anneal it, they grow into size of about 112 nanometers. So we identify this growth to be an Ostwald ripening process to grow these particles, and also we can control different thickness by depending upon how many cycles we use to deposit. We have made solar cells to show you the thickness dependence, and we find that about 300 to 400 nanometer is an optimal thickness to get the maximum power conversion efficiency. If the thickness is too small, then you get a lot of pinholes. As a result, if the film is not continuous, the quality of the film is poor, so we get poor efficiency. So in this case, at that time, we got about 5.5% efficiency with these solar cells prepared with the cesium lead bromide crystals. And soon later, there was a paper from NREL group came out with the efficiency of 13.4%. They use cesium-lead iodide quantum dots, and they use a washing technique. In our technique, we anneal to remove ligands. In this case, they washed to get rid of the ligands to get it this one. Today, these cells are being talked about for making tandem type solar cells. In the tandem type solar cells, basically you try to harvest energy in different regions. For example, the right hand side picture shows you a silicon solar cell on which top of which you have put a perovskite solar cell. The high energy photons are absorbed by perovskite, and then near IR photons are absorbed by silicon, giving you some of the highest efficiencies that can be attained in these ones. So this is another active area which is a multi-junction solar cells. Again, in the top corner you see here the perovskite solar cell is put in front of silicon so that different region of the spectrum can be harvested by different solar cells, and they call it as a 4-junction solar cell. In the 4-junction solar cell, basically you are putting one solar cell on the top of the other, whereas in the 2-junction cell you really grow the second layer on the top of the first, and there are only 2 contacts to make it. The theoretical prediction is one should be able to get 36 to 38%. Note that silicon has only 26%. It is basically stuck around that area, that value, and we need to find ways to improve the efficiency, and the multi-junction solar cell is one of these ways to make it. So that comes to the aspect of, again, making mixed halide lead perovskite, as one can use again the composition of halides to tune the band gap of material. And in the bottom of this slide you see different colored solutions emitting light, and they range from anywhere from 700 nanometer peak emission to 400 nanometer peak emission, and these correspond to the cesium lead chloride, bromide and iodide, along with mixed halide containing both chloride and bromide, or bromide and iodide. So this is a very interesting property that one can use to tune these properties. Another way to design these particles is you make one class of, say, chloride, and then treat with methylammonium bromide, and you get a bromide particles, or treat with iodide, you make iodide particles. So this is sort of exchangeable halide ions, allow you to get different compositions. So there are various techniques people use to make it. The goal is to make different band gap materials so that one can use them in a tandem architecture. So there are 2 ways of doing this. One is what we call gradient architecture. Say for example you take a cesium lead bromide film and expose it to iodide just enough to get a gradient structure. So at one end you have iodide, other end you have bromide. So when the white light strikes, the blue light is absorbed by the cesium lead bromide, and the green light is absorbed by the mixed halides, and the red light is absorbed by the cesium lead iodide. So this way you can harvest energy in the different region of the film. The other possibility is having a layered architecture. So you first put a layer of iodide, then a mixed halide, and then a cesium lead bromide. So again, one can come up with these strategies to harvest photon with greater efficiency in these ones. But there are some problems like halide ion exchange, and that needs to be suppressed in this case. So if you are working in the area of research perovskite solar cell, here are some of the opportunities that still needs good understanding how and why these things happen. I just mentioned to you how we can tune the band gap with composition with these materials, but there are also now low dimensional perovskites like 2D and 0D perovskites, so they are coming into play. Another one area that is important is lead-free perovskites. People are trying to replace lead with tin, but they are highly unstable. So are there any other metals that one can use? Same way, mixed halide systems, trying to understand the halide ion mobility and minimize the phase segregation effects. Surface treatment has known to play a greater role because it has full of surface defects, and any remediation of these defects leads to a better performing semiconductor nanostructures. Another aspect is cation migration that also leads to the instability. These materials can also be used in LED and other optoelectronic devices. And finally, the tandem solar cells. So these are just give you a brief list of opportunities where one can pursue further research. So to summarize, quantum dot architectures are excellent choice for light energy conversions, and these are still show excellent properties, and the ternary and quaternary semiconductor quantum dots offer new opportunities in the same direction. Metal halide perovskites facilitate design of tunable display devices, and one needs to explore more in this direction. And finally, the nanostructure design can play a role in boosting the performance of tandem solar cells. And here are some examples, a list of papers then you can follow through for better understanding of the process. Finally, I would like to thank all the researchers. There have been students, postdocs, visiting scientists, collaborators. These are only a few names of current group, but there are many of these people have contributed to our research and better understanding of these processes. I would like to thank each and every one of them. Without their help, we wouldn't have been succeeded in this area.